Okay guys, so in this video we are going to look at some examples on how we can apply the calculations on frames and machines. So if you look at this particular structure, it is actually a frame consists of two members of AB and BC. So you're required to find the horizontal and vertical forces of pin C. So you know C is a pin type of joint, so there will be one force in the Y direction and another force in the X direction. So basically they want to know what is the magnitude of CX and what's the magnitude of CY. Okay, let us try to solve this particular problem by drawing the free body diagram of each individual members. Okay, so you know there are two members of this particular frame, which is member AB and member BC. So this would be the AB member and this would be the BC member. Let's just label the joints accordingly so that we don't get confused. Okay, so we know at joint C there's a vertical force called Cy and there's a horizontal force called Cx. Okay, and then if you look at joint B, it connects between member AB and member BC. So if there's a connection kind of joint over there, then the direction of the force would depend on the neighboring member. Okay, the direction of the neighboring member. So I'm going to call this FAB, and the reaction force at the other member would be in the same magnitude but with a different direction like this. Okay, and then don't forget this downward vertical force of 2000 Newton in the middle of member BC. Okay, now what else? Okay, look, there's at joint A, it's a pin kind of joint. So by right, there are two reaction forces over there, which is the AY and also the AX. Okay, I think that is all the external forces acting on the individual members. Okay, now you have the choice to either solve it from member AB or from member BC. But then there are so many unknowns at member AB, so there's no point of solving it from member AB. So at the same time, the question actually asks you the horizontal and vertical force at point C. So they want to know what is the magnitude of CX and CY. So in this case, it's much better for you to solve this problem from the member BC. Okay, so let's apply the equilibrium condition for moment at point C so that we can cancel out the two unknowns of Cx and Cy and find the magnitudes of FAB. Okay, so recall the formula for moment is equivalent to Fd. Okay, this 2000 Newton multiplied with the perpendicular distance to rotation point C, the distance is 2 meter, and if you draw an imaginary circle around point C, you'll get a counterclockwise direction. So the magnitude of this expression is positive. Okay, now let's look at this FAB. FAB ni sangat bengek kan, so you can resolve it into an equivalent X and Y direction. So we need to know the angle at this one corner. So let's look at the original diagram. If you draw a triangle over here, this angle is 60 degrees. So the angle of this tiny space here will be 90 degree minus 60 degree, and the remaining angle is 30 degrees. So our theta is 30 degree. Okay, now we can resolve this FAB into an equivalent Y direction. It will become FAB cos 30, and if we resolve it into an equivalent X direction, it will become FAB sin 30. Okay, boleh proceed this analysis for moment calculation. Okay, this FAB cos 30 will create moment, and the perpendicular distance to rotation point C would be 2 meter plus 2 meter become 4 meter. Okay, and if you draw the imaginary circle around rotation point C, the direction is counterclockwise, so the magnitude of this expression is positive. Okay, how about FAB sin 30? Okay, there will be no moment created by this particular force because it passes through the rotation point C. Okay, that's basic. So kalau dah tak ada lagi, all this expression would become equivalent to 0. So you can easily solve for the unknown variable, which is FAB. Use your calculator and you will get the magnitude of FAB to become negative 1154.7 Newton. So it simply means that the magnitude of FAB is actually 1154.7 Newton, but the direction is in the opposite direction like this. Okay? Anyway, if you want to avoid confusion, you can just leave your question in negative form like that. Why? Because if in the future analysis, you are going to refer to the same direction of your initial assumption, kan? So, you can just leave it as it is. Tapi yang penting, bila ada calculation, you kena masukkan the magnitude of negative because you are referring to your initial assumption, okay? Okay, now let's apply the equilibrium condition in the x direction pula. Okay, so there is one force in the x direction, which is the cx. So the direction is to the right, so the magnitude is positive. And then there is another force in the x direction, which is this one, FAB sin 30. But again, remember, like I said earlier, this is your initial assumption kan? So, when you masukkan the magnitude of FAB, masukkan the magnitude of negative kat dalam tu because it is based from your initial assumption. Okay? Okay, so you can easily solve for this particular equation as there is only one unknown, which is the Cx value. So use your calculator and you will get the magnitude of Cx to be negative 577.35 Newton. So it's okay kalau dapat negative, no problem. It simply means that the actual magnitude is 577.35 Newton, but the actual direction is pointed to the left. Okay? As the final step, let's apply the equilibrium condition in the y direction pula. I think you should master this technique very well lah. We've been repeating it every single exercise. Okay, so try to do this on your own. You will get the magnitude of Cy to be 1000 Newton and the direction of Cy is upward. Okay, dah siap. Okay, now let us look at the second example. In this example, given that the mass of the elevator car is 500 kg, if we want to convert that into an equivalent weight, then we have to multiply 500 kg with the gravitational acceleration of 9.81. Macam mana dapat formula ni? Okay, basic physics whereby W is equals to mg or ma. Okay, use your calculator and you will get the corresponding weight of the elevator car to be 4,905 and the unit is in Newton. Okay, stated here is that the elevator car is moving at a constant speed. Okay, walaupun it is moving, but it is moving at a constant speed means there are no acceleration. If there are no acceleration, then you can apply the concept of equilibrium to solve for this kind of problem. So you are required to find the force developed in the two cables. Betul ke ada dua kabel? Nampak macam banyak je. Okay, let me sketch the cables over here. This blue line here indicate one cable connecting through here. And this pink line is another cable connecting through here. Oh yeah, betul. So there are two cables in this particular elevator car machine. Okay, before we proceed with the analysis, if you notice at the elevator car, there's like a contact point to the wall over here at this 4 point. So basically, this contact point doesn't allow the elevator car untuk move senget-benget. So if it doesn't allow any kind of movement in that direction, supposedly there is a reaction force acting against that particular direction like this. So we are going to call that force as N. Okay, cool. Now, I am going to apply the method of section to identify the tension force developed in the two cables. Okay, remember the method of section. Imagine that you potong the system into multiple sections. So, in this case, I'm going to potong it into one elevator car punya section and another one is based on pulley C. Okay, because kenapa pulley C? Because pulley C tu ada dua cable connected to it, which is cable warna biru tu and another cable which is a pink coloured one. Okay, now we are going to draw the free body diagram of each section. Okay, in this case, let's draw the free body diagram of the elevator car. So this is our boxy elevator car and this elevator car is connected with pulley over here and another one over here. Okay, so we know the weight of the elevator car is acting at the center of the elevator car with a magnitude of 4905 Newton. And then there is a reaction force at the sides of the elevator car. Let's call it N1. This one as N2. This one as N3. And this one as N4. Okay, at the right side of the pulley, there is a blue colored cable over there. So there is a tension force. We'll call it T1 over here and another T1 over here. And also the cable is connected connected at this particular point. This is also another T1. Okay, so at the left side of the pulley is a pink colored cable. So we are going to call it T2. This side is also T2. And ada lagi tak? Is it connected to any other points? No, it's only connected at that 2 points only. Okay, we can't really apply the equilibrium condition in this particular free body diagram because there are many unknowns. Ada T1, ada T2, ada N1, N2, N3, N4. So, you just need to construct another free body diagram. Okay, this time around, I'm going to construct the free body diagram at pulley C. Okay, now I'm going to sketch pulley C like this. Boop, 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 boop. And if you look closely at pulley C, at the left and the right side of the pulley, it is connected to the blue colored cable. So we are going to represent the tension cable over here. And at the middle point of pulley C is actually the pink colored cable. So we are going to represent the tension cable over here. Okay, so back to our free body diagram. This is going to be our T1, and on the left side is also another T1. And there's a pink colored cable adjoined at pulley C, which happening at this particular point, and we're going to call it T2. Okay, the free body diagram of this pulley C looks quite simple, kan? So, if we apply the equilibrium condition in the y direction, so we can get an expression whereby summation of all forces in y equivalent to 0. So, T2 is positive minus 2T1 is equivalent to 0. So, we can get an expression of T2 whereby T2 is equivalent to 2T1. Okay, still tak solve lagi the equation. So, we are just going to call this particular equation as equation 1. So, now let us apply the equilibrium condition for the free body diagram at the elevator car pula. Okay, so if you apply the equilibrium condition in the y direction, so you know there is a negative 4905 acting downward, and then there is 2T2 over there, so plus 2T2, and there are 3T1 over there acting upward, so that is 3T1. So all this expression sums up to 0. So recall from equation 1, T2 ni sama dengan 2T1. So you just substitute the value of T2 into this equation. So this equation is being simplified to only have one variable or one unknown of T1 sahaja. Okay, so negative 4905 plus 2 multiplied with 2T1 plus 3T1. Okay, so you see, cuma ada satu unknown variable which is T1 sahaja. So you can easily solve for this particular equation, and you will get the magnitude of T1 to be 700.7143 Newton. Okay. Okay, so quite conveniently, you can substitute the magnitude of Ty of 700 Newton into equation 1. So, you will get the magnitude of T2 is equivalent to 2 multiplied with T1 of 700.7143 Newton. And you will get the magnitude of T2 to be 1401.4286 Newton. Or you can also convert this into an equivalent kilonewton value, whereby you get 1.4 kilonewton, something like that lah. Okay, so dah siap. Okay, so let us look at this final example. So given that the smooth disc, which is connected at point D, has a weight of 200 Newton. So there is 200 Newton force acting downward. Okay, and you are required to find the horizontal and vertical components of reaction at pins B and D. Anyway, before we proceed finding all the reaction forces at pin B and also point D, so let us draw the support reaction happening at each joint. Okay, so you know at this A is a pin kind of joint, so there are two corresponding forces, which is the vertical force of AY and the horizontal force of AX. Okay, and C is a roller kind of joint, so there would be one reaction force in the X direction. We're going to call it CX. Before we look for the magnitudes of the forces at the joints, so let us first solve this free body diagram for the entire body and look for the magnitudes of the support reactions. Okay, so in the first step, I'm going to apply the equilibrium of moment at point A, because there are many forces acting at point A. I want to cancel out many unknowns over there. Okay, so if we convert this particular force into an equivalent moment, so 200 Newton multiplied with the distance to the rotation rotation point A. So you know the punya radius is 0.9 meter, and if you draw an imaginary circle around rotation point A, the direction is clockwise. So the magnitude over here will be negative. Okay, so accordingly, if you convert the Cx into an equivalent moment, the force is Cx, and the distance to the rotation point is 1.05 meter. And again, if you draw the imaginary circle around rotation point A, you will get the direction to be counterclockwise. So the magnitude of this particular expression is positive. Okay, ada lagi tak? Tak ada. Okay, so the summation of these two expressions will become equivalent to 0. So as you can see, there is only one unknown in this equation. So you can easily solve for Cx, and you will get the magnitude of Cx to be 171.43 Newton. And if it's positive, it means our initial presumed direction is correct. So the direction of Cx is to the left. Okay, cool. Now we can apply the equilibrium condition in the x direction pula. Okay, so there are two forces acting in the x direction, which is this ax and also this cx. Okay, so you put these two expressions in your equation, and this sums up to 0. So remember, we already calculated the cx to be 171.43 Newton. Okay, just masukkan je dalam equation, and you will get the magnitude of ax to be negative 171.43 Newton. So negative means that the direction of AX is actually to the right. Okay? So accordingly, you can calculate the magnitude of AY by applying the equilibrium condition in the Y direction pula. Okay? So along the Y direction, there is one force of AY over here and another force of 200 Newton over here. So you just substitute that two items in your equation, and that sums up to 0. Okay, so easily you can solve for AY, and the magnitude of AY would be 200 Newton, and the direction is upward. Okay, now that we have found all the magnitudes of the support reaction forces, the next step is barulah you boleh analyze this particular structure for its member. Okay, so this frame consists of 3 members. Okay, this semicircular structure over here, this smooth pin over here, and this L-shaped member. Okay, now let's label the individual members accordingly. This is joint A, this is joint B, this is joint D, and this is joint C. And remember, this point is connected to joint D. Okay, and then don't forget the point B over here. Okay, now let's draw the reaction forces at each joint. Okay, at joint A, you know there is a vertical force of AY, and the magnitude we already calculated to be 200 Newton. And then there is another horizontal force acting at point A in this direction, and the magnitude is 171.43 Newton. Ini yang kita kira tadi kan. And then at point B, okay, point B is connected to the L-beam. Okay, so if it is a pin connected, accordingly, it can be resolved into a horizontal and vertical force. So if this is Bx, this is going to be our By. So at the neighboring point B, which is at the L-beam, so it will be a couple force. It will be in the same magnitude but with the opposite direction. So if Bx from one side is to the right, then the Bx on the other side will be to the left. Okay, sama juga macam By. Kalau By from the semicircle is upward direction, so By at the L-beam will be downward direction. Okay, at point C, we know there is a horizontal force in this direction. We already calculated it earlier, and the magnitude is 171.43 Newton. Okay, and okay, at point D, there is a weight of 200 Newton acting at point D, and then this point D is pin connected to the L-beam. Okay, so if it is pin connected, then there will be one dx over here and another dx at this point in the opposite direction. Accordingly, there will be one dy over here, and there is also another dy at this point in the opposite direction. Okay, now let's zoom at this part closely. So if you notice, the smooth pin is touching to the semicircle beam. Okay, so if it is touching, walaupun dia touching, there should be a reactive force at that particular point. Okay, so there would be one vertical force in this direction. So if we assume the direction at smooth pin D to be upward direction, and at the semicircle, it should be in the same magnitude with the opposite direction. So we are going to call it N. Okay, now I believe all the reaction forces at each individual members are complete. Okay, barulah kita boleh proceed with our analysis. So you have the choice to either solve it from member AB or from member BCD or from the smooth pulley D. Okay, it's up to you. But then look back at the question. The question asks you to find the force, the reaction force, the horizontal and vertical reaction force at pin B and pin D. So kalau kita tengok pin B ni ada dekat member AB. So let's just try to solve this particular free body diagram from member AB. So, focusing on member AB, let us apply the equilibrium condition in the x direction. Okay, in the x direction, there are two items, which is the 171.43 Newton and also the BX. You put that into your equation and you can easily solve for BX to be negative 171.43 Newton. Okay, jangan risau pasal negative. Negative simply means that the magnitude is 171.43 Newton, but the direction is actually opposite to the one that you initially assumed, which is to the left. Now the next step is that we are going to apply the equilibrium condition for moment at point B. Kenapa point B? Because I want to cancel out the many unknowns at point B. Okay, so applying equation of moment at point B, summation of all moment at point B equals to 0. You try to do this on your own, and at the end of the day, there will only be one unknown in your equation, which is the N magnitude. Okay, so at the end of the day, the N will become 400 Newton and the direction is downward. Okay, finally, we can apply the equilibrium condition in the y direction pula. Okay, you just substitute all the forces acting in the y direction, and then there are By and there are also N. Tapi ingat, N tadi kita dah kira kan 400 Newton acting downward. So you just substitute that into your equation and you will get the magnitude of By to be 200 Newton and the direction is pointed upward. Okay, back to our main question. Tadi dia minta the vertical and horizontal force reaction at pin B and D. Tadi kita dah cari the magnitude of BX and BY. It's done. So our next mission is to look for the vertical and horizontal reaction force at pin D. Or in other words, we have to find what is the magnitude of dx and dy. So it's up to you whether you want to solve it from the pulley or you want to solve it from the L-beam. So I think in this case, I want to try and solve it from member BCD, from the L-shaped member, okay? Okay, sebab my drawing board dah tak muat, I'm going to continue for the third step at this upper side here. Okay, so now I'm going to solve at member BCD and I'm going to apply the equilibrium condition in the x direction pula. Okay, so there are three things in the x direction, which is the dx, the bx and also the 171.43 Newton. Okay, so recall bx tadi kita dah kira awal-awal tadi, which is this one. We are going to take the negative value into our equation because we are following the direction that we initially assume. Okay, so based from this equation, there will only be one unknown, which is the dx. So I can easily solve for dx and the magnitude is 0 Newton. So there are no forces acting in the dx direction. Okay, so accordingly, the next step is we are going to apply the equilibrium condition in the y direction pula. Okay, so there are only two items in the y direction, which is the dy and also the by. So just put that into the equation. By tadi kan kita dah kira over here. So the magnitude of by is 200 Newton. Oh, sorry, I ada silap tulis sikit dekat situ. In the equation, it should be tolak 200. Okay, sebab kita follow the previous equation tu. So, at the end of the day, the magnitude of dy is negative 200 Newton. So, it simply means that the magnitude of dy is 200 Newton, but the direction is pointed upward. Okay, dah siap. Okay, that is all for now. We've reached the end of chapter 6, which is structural analysis. I hope I am able to deliver the content of this topic effectively, and I hope you managed to attain good understanding in this chapter. So don't forget to fill out the e-attendance form, and also don't forget to do the tutorial provided in ULearn. So till then, see you later, alligator.